Hello and welcome to this section on kinetics, in which we have 3 video lessons and a required practical as well. So the first video lesson is this one on reaction rates, and the specification reference is 3.1.5.1, 0.2, 0.3 and 0.4. So let's look at our learning objectives, of which there are many, each of which is quite quick, but the first one is that we want to understand that reactions can only occur when collisions take place between particles that have sufficient energy. Okay, and that energy is called the activation energy. Activation energy, the minimum kinetic energy required for two particles to react together. Okay, what we also want to do in this little video lesson is we want to define the term activation energy, which we've just done in fact. So we also want to be able to explain why most collisions do not lead to a reaction. And we want to understand the Maxwell-Boltzmann distribution. Also, we want to be able to draw and interpret distribution curves for different temperatures. So that's Maxwell distribution curves at hot and cold temperatures. And we want to understand qualitatively the effect of temperature changes on the rate of reaction. Also, use the Maxwell-Boltzmann distribution to explain why just a small increase in temperature can lead to a large increase in reaction rate. And we'll also understand the qualitative effect of change in concentration on free and collision frequency. And also explain how a change in concentration or pressure, they're very similar, how a change would influence the rate of reaction. So that's our learning objectives. Okay, so first let's have a look at collision theory and activation energy. Firstly, collision theory, and there's two elements to collision theory. So for a reaction to happen, two particles have to collide, and they need to collide with the correct orientation. So that's the first element of collision theory. But also, even if they're correctly oriented, they also need a minimum amount of kinetic energy when they collide, because the bonds that are in the reactants need to be broken, and they're broken by the force of the collision, and that force depends on the kinetic energy the particles have when they collide. So let's write minimum kinetic energy. So they're the two elements to collision theory that determine whether a collision is going to lead to a reaction or not. Okay, so that's collision theory. Let's just think about activation energy, and we've mentioned this a couple of times now. Activation energy is the minimum kinetic energy required for two particles to react together. So it's the minimum kinetic energy required to break the reactant bonds such that they may then react. So we'll write it down, minimum kinetic energy needed for particles to react. Okay, so we're going to develop these two little concepts by looking at a graph. And on our y-axis, we're going to have enthalpy. So we're going to have enthalpy, and on the x-axis, we're going to have progress of reaction. And by that, we just mean we're going to go from reactants to products. So the reactants are going to have a certain level of enthalpy. Let's give it this amount of enthalpy. So they're going to have that amount of enthalpy, and they're going to have this sort of reaction path here. So that what we've got here is we've got reactants, and here we've got products. And let's explain the curve as we go along. So this is during a reaction. So what's happening at this point in the curve here is that the particles are colliding, and the bonds within each particle are being stretched and to breaking point. Right. So during a collision, bonds in the reactant particles, they're being stretched. And right up here, so let's draw ourselves a little dotted line. It's supposed to be a straight dotted line. Right up here to this level of enthalpy is where the bonds have actually broken. The bonds have actually broken, so the particles that exist at that stage are very unstable and have high enthalpy. And what we're also going to do is we're going to draw a little dotted line out from the initial enthalpy. Yeah, so then we can draw an arrow here, because this amount of energy to go from the level of enthalpy that the reactants had before the collision to the level of enthalpy that the intermediaries have when all the bonds are broken, but none of the bonds are formed. Right, that increase in enthalpy is equivalent to the activation energy. Right, so that kinetic energy that was in the colliding particles has been transferred into enthalpy, so the enthalpy level of the intermediaries, i.e. the reactant particles that have had their bonds broken. That's the activation energy, that amount of energy there. And that's the energy barrier that the particles have to overcome before they can react. So at this point in the curve here, the intermediate particles, they're so unstable they can't exist by themselves for anything longer than an instant in time. So they form new bonds. So let's write that down as the intermediaries, or the intermediate particles. They are now forming new bonds. And that releases energy. Such that when you get down to the when they've completed their new bond formation and they've formed the products, the enthalpy left in the products is less in this case, because we've drawn a graph. It's called an enthalpy profile diagram for an exothermic reaction. And so the last thing to just highlight is the decrease in enthalpy. So we call this the enthalpy change here. So that's the enthalpy change between reactants and products. And it's the enthalpy that we started off with the reactants. the difference between that and the enthalpy that we finish with the products. So I think the last thing to say about this enthalpy profile diagram is that if the activation energy is large, like I've drawn here, that activation energy is large, and what that means is that only a very small number of the particles are going to have enough kinetic energy to provide that activation energy and make the collision a successful collision that results in a reaction forming products. So only a very small number are going to have the kinetic energy equivalent to the activation energy. Whereas if the if the activation energy was much less, I'll just draw that here in for us. So if we had a reaction which was more like that, so we start at the same point of enthalpy and we finish at the same point of enthalpy, but the activation energy for this, just put AE for activation energy, if the activation energy is small, then you can clearly see that it's more likely that many more of the particles will have that smaller activation energy in order to react, and so the reaction is more likely to happen, and it will happen at a faster rate as well. So that last comment about some particles having lots of energy, i.e. enough energy to react, and other particles having less energy, leads us on nicely to the next topic, which is the Maxwell-Boltzmann distributions. So here we have Maxwell and Boltzmann. The top one is Maxwell. He was Scottish, and this fellow at the bottom here with the big black beard was Ludwig Boltzmann. He was Austrian, and they came up with a distribution curve, which is really a model that explains scientific. It's a theoretical model that explains scientific observations, and what it does, it looks like this. Okay, so again we've got axes, and this time on the y-axis we're going to have number of molecules. So number of molecules on the y-axis, and we're going to plot that against kinetic energy. So low kinetic energy on the left and high kinetic energy on the right, obviously, and small numbers of molecules at the bottom and a large number of molecules at the top. And we're going to draw a curve, and our curve, let's draw a curve in blue. So I'm going to attempt to draw a curve here that represents that's sort of right, that's okay. So that's the shape of the Maxwell-Boltzmann curve, and what we're going to do is we're just going to highlight different areas of the curve. So at the point 0, 0, the interesting point about that is that there are no particles with no energy. So no molecules have zero energy. So it needs to. So our curve needs to start at the origin. And then there are a few molecules here. Let's look at this area of the curve there. Here, there's going to be a few molecules that are slow moving. So a small number of molecules that are moving slowly, and there's also going to be a small number of molecules that are moving very fast. And if they're moving very fast, of course, they have a high amount of kinetic energy. But then, of course, most of the molecules, most of the molecules have a medium amount of kinetic energy or are moving at medium speeds. Most of molecules have, let's call them medium speeds or medium kinetic energy. So at this point in the curve here, right at the top, we're going to draw a little dotted line down to the bottom of the x-axis, and because that point there is the point that tells us the kinetic energy of the most of the molecules, kinetic energy of most molecules. Okay, in maths that would be equivalent to the modal average. And that's not quite the same as the mean, because whilst we can't have any less kinetic energy than zero kinetic energy, we can have a very high kinetic energy. So that skews our mean to the right of the mode. Right, so the mean is likely to be at this point here. So that might be the mean kinetic energy of the particles. And I think the last thing to say about a Maxwell-Boltzmann distribution is, and this may be obvious, if it's not, it's worth saying, is that the area under the curve is equivalent to the total number of molecules. Okay, so the total number of molecules. So if you're going to change the temperature, but you're going to keep the same number of molecules, the shape of your curve would change, but the area under the curve would stay the same. Okay, so actually the last thing is to talk about activation energy. So let's switch color because that's an important part. So for a given reaction, there is going to be an energy that is the activation energy. And let's say it's this energy here. All right, so let's write that in red. So we're going to call this the activation energy. So that's if that is the activation energy, then all of these molecules here have kinetic energy higher than the activation energy. So they are the ones that if they collide in the correct orientation, they can react. Okay, so these are the particles that have enough kinetic energy to react if they are also oriented correctly. Okay, so that's the Maxwell-Boltzmann distribution. Let's have a look now at what happens when we change the temperature. So in order to look at the effect of temperature on reaction rates, we're still going to have a Maxwell-Boltzmann distribution. So let's redraw our graph, and you might remember that the y-axis is number of molecules, and our x-axis is kinetic energy. And we have a small number of molecules at low kinetic energy and a small number at high kinetic energy, and most of the molecules have a medium amount of kinetic energy, so that's why we get that graph with a peak in the middle that starts off in the origin. So what I'm going to draw first in blue is a curve for a lower temperature. Alright, so let's say that's 25 degrees C. Okay, and what I'm also going to try and do is I'm going to try and draw a curve for a higher temperature. So it's the same system, so the same number of particles. So I want the area under my curve to be the same, but it's going to have to shift to the right because more particles are going to have more kinetic energy if it's at a higher temperature. So hopefully what that looks like is that the amount of blue that's above the red at lower kinetic energies, the area in that section is similar, or it's supposed to be the same as the amount of the area of red above blue on the right hand side of kinetic energy, because the number of particles are the same. But obviously with a higher temperature, let's say 35 degrees C, at a higher temperature, more of the particles are going to have more kinetic energy. So let's just make that quite clear. At higher temperatures, more particles have more kinetic energy. By definition, as it happens, because it's the kinetic energy of the particles that gives something its temperature. Temperature is just a measure of the average kinetic energy of all the particles. So let's draw in black, let's draw in our activation energy. So let's say our activation energy was this energy here. So that energy there is our activation energy. Okay, so what we see, let's switch to blue, what we see is that this area here that I'm shading in now represents the number of particles that have the activation energy or more in the system that is at 25 degrees C. And what I'm going to do is switch to red and draw in this area here. So that's to take in the red from the red line down, so it includes the blue level. So we've got many, what we're going to say is there are many more particles that have the activation energy at 35 degrees Celsius. And a point to be made here, and I'll switch colour to purple, a point to be made is that a small increase in temperature so a small increase in temperature, here we've gone from just 25 to 35, so just 10 degrees increase in temperature. You can see that the way that the shape of the curve changes means that many more particles, like there's at least twice as many, there's probably 3 times as many particles have activation energy or more at 35 compared to 25. So we say that a small increase in temperature leads to a large increase in the number of particles with sufficient energy to react. And what follows on from that, of course, is that if there's many more particles with sufficient energy to react, that small increase in temperature leads to a large increase in reaction rate. So that was the effect of temperature on reaction rates by looking at Maxwell-Boltzmann distributions. What we're going to do now is use Maxwell-Boltzmann distributions to look at the effect of concentration or pressure on reaction rates. So the effect of concentration on reaction rates, and for concentration you can also read pressure if it's a gas. Okay, so what we want to do is we want to draw our same Maxwell-Boltzmann distribution. So by now, of course, you remember that we've got a number of particles or a number of molecules. versus kinetic energy. And this time what I want to draw is I want to draw a curve, firstly for low concentration and secondly for high concentration. So in this case, unlike with temperature, in this case the number of molecules is not going to be the same. All right, so if we've got the same volume of container and we have in the first one a low concentration of particles, there's going to be a smaller number of particles. Whereas in the second case, if we've got same volume but high concentration, that means the number of particles is higher. So if the number of particles is higher, that means the area under our curve is higher. So anyway, firstly, let's draw the low concentration curve. So it's basically the same shape of curve, except it's got a small number of molecules in it. So we draw it like that, and let's label that low concentration. Okay, and now what I want to do in a different color is high concentration. So it's actually going to be same shape like that. So the area of the curve is greater, and this is high concentration. That's high concentration, and so therefore what we can see is that increasing the concentration has increased the number of particles, and that's illustrated with the area under the curve. So let's draw on our activation energy. Let's say this is the kinetic energy that's equal to our activation energy. That's our activation energy, and so we draw our dotted line vertically up so that we see that the number of particles at low concentration is that area of the curve there, and just by increasing the concentration we are increasing the amount of particles that have the activation energy. And that's logical, isn't it? Because if the particles are squeezed together, they're going to collide more frequently, and even if they have an even chance, because they're at the same temperature, even if they have an even chance of that collision being successful, because there are more collisions, because they're more tightly packed together, then more of those collisions are going to result in a reaction. So that explains logically what we've drawn here in the chart. So that's the last bit of content for this video lesson. Last thing remains is to review our lesson objectives. So let's see, what was the first one? The first one with this is that we wanted to understand that reactions only occur when collisions take place between particles that have sufficient energy, and that energy is called the activation energy. So we definitely did that. Then here's a few. Then we wanted to be able to define the term activation energy, and we did, if you remember, define activation energy to be the minimum kinetic energy required for two particles to react. And then we wanted to explain why most collisions did not lead to a reaction. Well, you saw from the Maxwell-Boltzmann distribution was that most of the particles don't have the kinetic energy that is at or above the activation energy, and also even if they did, they're not necessarily oriented correctly when they collide to make a reaction. So let's give ourselves a tick for those two. Then we wanted to understand the Maxwell-Boltzmann distribution. I hope you did that when we went through it a few times, and we interpreted distribution curves for different temperatures, and the key there was that the area under the curve was the same for the temperatures because it's the same number of particles, but it was the high temperature was skewed to the right, and that meant that a small increase in temperature led to a large increase in reaction rate. And then the last few, I think, are we wanted to understand the qualitative effect of temperature changes on the rate of reaction. We've just done that in the previous bullet point. And then use the Maxwell-Boltzmann distribution curve to explain why a small temperature increase leads to a large increase in rate. We've done that as well. And then we wanted to look at concentration on collision frequency. So we drew the Maxwell-Boltzmann distribution, and this time the area under the curve was not the same because we were dealing with the same volume of container, but we increased the concentration, so the number of particles was the same. And what we said there was that because the particles are colliding more frequently, you'd get more successful collisions, and also because there are more particles, by definition, more of them will have the kinetic energy at or above the activation energy. And last one, we wanted to explain how a change in concentration or pressure influences the rate of reaction. Yes, we've done that too. So hopefully they're all clear, and as usual, if not, re-watch the video and come and see me. Anyway, I'll see you in class.